This video helps to understand what is hybridization. This concept was introduced by the scientist Pauling and Slater to supplement the valence bond theory. The main features of hybridization are atomic orbitals of almost equal energy undergo hybridization or mixing. Those orbitals which are undergoing mixing will have nearly same energy and it is belonging to the same atom or ion that is taking part in hybridization. Another important point is that the number of hybrid orbitals formed is always equal to the number of atomic orbitals which are undergoing mixing. The hybrid orbitals are having similar geometry, but they differ in the orientation in space. Remember, hybrid orbitals form only sigma bonds and hybridization occurs only at the time of formation of a bond, that is in the formation of a molecule. Now we shall see the different types of hybridization. First, I'll take an example. Suppose I want to discuss the geometry of beryllium chloride. First, we have to identify which is the central atom here. You know, beryllium is the central atom. According to VSEPR theory, this molecule is of the type AB2. That means it is having a geometry which is linear in shape with A at the center and B arranged at an angle of 180 degree. So then it is proposed to have a linear structure. We'll check whether it is coming to linear geometry according to hybridization. The molecule taken here is beryllium chloride. So beryllium is the central atom. So write down the configuration of beryllium in the ground state. So the ground state electronic configuration of beryllium would be beryllium has filled orbitals in 2s. So then only if you promote the electron from 2s orbitals to the next vacant orbital, that is the 2p orbitals, we'll get the required number of unpaired electrons, for which we need to promote one of its electron to the 2p orbital. So in the excited state, you find that the electron from 2s is promoted to the next higher vacant orbital, that is the 2p, which will give you the configuration 1s, 2, 2s, 1. And 2p1. Now mix up the two different orbitals. Here you find that one unpaired electron is present in the s orbital and the other in the p orbital. So when we mix up these together, we say that it is undergoing hybridization, and the hybridization occurring here involves one s orbital and one p orbital, leading to two different sp hybrid orbitals, and then we say that the hybridization occurring here is known as sp hybridization. That is, when one s orbital mixes with one p orbital, it would lead to the formation of two different sp hybrid orbitals, and the resultant hybridization is known as sp hybridization. And when we check the character of the hybrid orbitals, you find that out of two orbitals that are obtained, one is s character, so it is having half the s character and half the p character. You know that S is spherically shaped and P is dumbbell in shape. So if it is having half of S character, that means 50% S character and 50% P character. And you find that in that we have two unpaired electrons which are arranged. You know that they will be arranged in space far apart. So then you find that the hybrid orbitals will be arranged in such a manner that the first sp hybrid orbitals will be arranged like this. The second one will be joining here in almost opposite to the other one with an angle of 180 degree. So here this is the hybridized state of beryllium. So beryllium is having two unpaired electron and that is combining with chlorine. You know that chlorine belongs to the 17th group. It is a p block element. Evidently the outermost electron will be present in the p orbital. So the p orbital of the higher chlorine atom will overlap here, resulting in a sigma bond. The second p orbital comes and overlap to the second side of beryllium, leading to two sigma bonds. So this is first chlorine, this is second chlorine. So both of them are leading to two sigma bonds. So the structure will look like Be, Cl and Cl. So it is at a bond angle of 180 degree. So the shape is linear. So what is predicted by VSEPR theory is found to be true in the case of hybridization too. So here you find that beryllium chloride is having a linear shape. Now we shall take another example of boron trifluoride. Which is the central atom here? It is boron. Boron, what is the ground state configuration? So ground state electronic configuration will be 1s2, 2s2 and 2p1. On examining the configuration, we are able to find only one unpaired electron. That means it is able to form only one sharing or one covalent bond. Here, according to the formula, we should have three covalent bonds. So this is of the type AB3. So we'll just check the VSEPR theory. In VSEPR theory, if it is of the type AB3, the prediction is A will be the center and we have the B atoms arranged at the corners of a trigonal planar with a bond angle of 120 degree. So the predicted structure according to VSEPR theory is trigonal planar. Now we'll check whether we are getting the same. So here with the ground state configuration, we are unable to form the molecule BF3, for which we have to do the excitation. So from where to where we have to excite the electrons. Here In order to create 3 unpaired electrons, the electron in the paired condition has to be promoted to the next higher orbital. So then the configuration will look like 1s2, 2s1, 2p2. Now on mixing the different orbitals, which are the orbitals that are to be mixed? One s orbital is mixed with two different p orbitals. So then the hybridization would be sp2. So sp2 hybridization will result in 3 sp2 hybrid orbitals. So on mixing one s orbital with two different p orbitals, we get 3 sp2 hybrid orbitals. And these 3 sp2 hybrid orbitals are almost having similar shape and geometry, and they have to be aligned at the corners of a trigonal planar structure. On checking the characteristic of the hybrid orbitals formed, you find that one s orbital is mixed to form 3 sp2 hybrid orbitals. So it is having 1/3 s character and 2/3 p character. So on converting it to percentage, you have 1/3 of 100, that is 33.3% s character, and 2/3 of 100, that is 66.6% p character. So it will have more of dumbbell shape compared to that of spherical shape. These 3 sp2 hybrid orbitals are directed at the corners of a trigonal planar. So you have the first orbital, second orbital, and the third orbital at an angle of 120 degree. This is the structure of boron. Boron is having 1 electron each, and that is combining with 3 fluorine atoms. Fluorine again belongs to halogen family. It is in the 17th group. So the valence electron will be occupying in a p orbital. So a pure p orbital is coming and overlapping here to form 3 different sigma bonds. 1, 2, and 3. So this is the structure of boron trifluoride. So according to the prediction, they have given the geometry as trigonal planar, and here after hybridization too, we get it as trigonal planar. So the hybridization involved is sp2. Now we will discuss the case with methane molecule. What is methane molecule? Methane molecule has a formula CH4. Which is the central atom here? It is carbon. Carbon, the ground state configuration will be 1s2, 2s2, and 2p2. So according to this structure, you find 2 unpaired electrons with which it can form only 2 covalent bonds. But in CH4, you find that there are 4 covalent bonds. That means 4 sharing is there. 4 covalent bonds are present. 4 covalent bonds means 4 unpaired electrons are to be created. So with ground state configuration, we cannot explain the formation of CH4, for which we have to excite the electrons, and from where to where the excitation occurs. Here you find that excitation occurs from the 2s electron to the 2p orbital. So the paired electron from 2s orbital is promoted to the vacant 2p orbital, which creates 4 unpaired electrons, and that leads to the excited state 1s2, 2s1, 2p3. So the promoted electron, I am showing it in different color. So you have created 4 unpaired electrons, so for which we are doing the intermixing of 1s orbital and 3p orbitals, leading to what is called sp3 hybridization. So if it is sp3 hybridization, 4 hybrid orbitals are created. The hybridization is known as sp3, and you find 4 different hybrid orbitals are produced. The 4 hybrid orbitals are aligned at the corners of a regular tetrahedral with an angle of 109 degree 28 minutes. So we can represent the structure as 1, 2, 3, and 1 orbital is behind. So you find that it is having a tetrahedral structure, and each orbital is carrying 1 electron, and that is shared with 4 different hydrogen atoms. Where do you find the electron in hydrogen atoms? It is in the 1s orbital. So you know that it is spherical in shape, and that is overlapping here with the carbon, and it is giving the structure 1 sigma bond, 2nd sigma bond, 3rd sigma bond, and the 4th sigma bond. So this is the structure of CH4. Bond angle is 109 degree 28 minutes, and the shape is known as tetrahedral structure. So the same shape is predicted according to VSEPR theory. In VSEPR theory, you find that CH4 belongs to the category called AB4. So here the 4 orbitals are to be placed, or 4 bonds are to be placed at an angle of 109 degree 28 minutes in order to minimize the bond pair repulsions, and the structure predicted is tetrahedral. There also you find the bond angle was predicted as 109 degree 28 minutes. So here you find that the hybridization involved in carbon is sp3. On checking the character of the hybrid orbitals, you find that 1s orbital is mixing with 3 different p orbitals, leading to 4 sp3 hybrid orbitals. So that would lead to 1/4 s character and 3/4 p character. On converting into percentage, you find that it will be 25% s character and 75% of p character. So then it will have more of dumbbell shape, and that is found to be true in the case of sp3 hybrid orbitals.